Okay, everybody, we're going to get started on 9.5, the logistic model. So first, we're just going to kind of discuss the basic model that we already know of population growth. So we know that the rate of change of population depends on the size of the population. That is to say that dp dt is equal to k times p, where k is some constant, okay? So if we assume the initial condition p of 0, so time 0 is equal to p naught, we can solve this equation as a separable differential equation, okay? So what I did here was I integrated both sides of the equation after I separated the p over to the other side and the dt over to the right-hand side. And we're left with ln of p is equal to kt plus c. So we're going to do our normal solving for p. So we get p by itself. We could rewrite this using exponential functions as well. And we get p is equal to e to the kt plus c. So all I did here was I rewrote this as, I took the addition and rewrote it as e to the kt times e to the c, which is the same as what we did right there. Now, we're going to say that e to the c is some constant. So let's call it a new constant, d. Okay, so then that's where this replacement equation came from, okay? If we assume, or if we use our initial condition of p naught equals to p of 0, then we have p naught is equal to d e to the 0, but we know that e to the 0 is just 1. So this means, so this is just 1. So this means that p naught is equal to d. So then I can replace d in my other equation with p naught. So this is where we get our population growth formula from. And that's pretty much the one all of you know. Sometimes it'll be A is equal to PE to the RT, also known as PERT. Some of you were taught it that way. So that's kind of our normal basic population growth model. But this population growth model has no bound. It grows without bound. So the logistic model is going to introduce the idea of carrying capacity. So for us, carrying capacity is what differs the logistic model from the regular population growth. So here's the thing. If you think about it, like a lot of times they, one of the models or one of the explanations they use is let's say that there's a high school of 2,500 kids and there's a rumor spreading at the high school and it follows the logistic model. Well, the carrying capacity of the rumor spreading to the high school is only 2,500 because you can never go more than 2,500 of the high school students because that's the total number of high school students. So the carrying capacity of that high school has 2,500 as its limit. That's the most you could ever do. So you can't spread a rumor to more than 2,500 kids at the high school if there's only 2,500 kids at the high school. That's what the logistic model is trying to deal with. So this is our formula we're going to work with. dp over dt is equal to kp or times 1 minus, or the quantity 1 minus p over m, where k is the constant and m is the carrying capacity, okay? So again, we will solve for p using our initial condition. So we're kind of going to go through the motions here. I'm going to kind of walk you guys through this, okay? So let's first make these have common denominators, right? So this would be dp over, let me write this better. dt equals k times p times m minus p all over m, right? However, we could now separate this and get all the p's on one side. Let's see if there's a, I'm going to keep the k with the dt. So then this will become, let's see here. How can I write this best? So this will become m, I'm going to multiply by the reciprocal, right? So I'm going to multiply this side by the reciprocal, which would be m over m minus p, and then times 1 over p. So this would cancel this would cancel this, and this would cancel this, right? But I also have to do it to the other side, but I didn't leave myself enough room. So we'll pretend I did it there. Sorry about that, you guys. So that means I'm going to have m over m minus p times, you know what, I can put the p right here, times P, and then I have dP still left. That's equal to K times dt, which is okay. Let me see. So what we could do here is we could take and we could clean this up by doing a little, I guess we could integrate both sides of this. So we're going to integrate both sides of this equation. Okay, and we know the right-hand side is going to be KT plus C, right? Now the left-hand side is going to be a little bit more annoying. If you want to do, I'll do a little scratch work over here on the side. Let's do it in green. Sorry about that. Let's do that in green. It's actually M over P times M minus P equals A over P plus B over K, oops, not K, M minus P. So we could do a little partial fraction decomposition, okay? And you guys, so I'm gonna put use partial fraction PFD to take care of this, okay? Let me see here. Yeah, so then we could rewrite this now as the integral. So once we do the partial fraction decomposition, we'll end up with 1 over P plus 1 over M minus P dP equals KT plus C. So all I'm going to do over here, you guys, is I'm going to recreate this right here. This I'm going to use partial fraction decomposition. I don't want to go through it right now, but you guys have learned how to do that already. And you can do partial fraction decomposition on that. You'll end up getting M equals A times M minus P plus B times P. When you go through and do all the work, you'll end up getting 0 equals, I think it's -2 plus 2B. So B equals 1, and then you can go from there and find A. But I'll trust you guys can follow through with that and finish that up using partial fractions. Okay, so now we have this integral. So we know that this guy is the ln of the absolute value of P minus this guy is the ln of the natural absolute value of M minus P. Because in this problem, because it's with respect to dP, M is kind of like a constant of like 5 or 7 or something like that. Okay, so KT plus C equals KT plus C. Okay, so now let's see where we're at. Let me see here. So you guys see that this is actually, I could factor out a negative. This is kind of, I learned this from somebody else. So this is, we could factor out a negative, and we could rewrite this as negative, and then we would have negative ln of the absolute value of P plus ln the absolute value of M minus P equals KT plus C. I could rearrange this. This would become ln of the absolute value of M minus P, oops, minus ln of P. Now this all is for a purpose. The purpose we're trying to go to from this is we are trying to get the this to be rewritten as the ln of the absolute value of M minus P all over P, and you'll see why in a second. Okay, so we have the ln of M minus P, but remember, we could technically split this, right? And we could divide the negative over to the other side. So this would now become, let's see here, this would become the natural log of the absolute value of M over P minus 1 equals negative KT minus C. Okay. Now we can E everything, or we can rewrite it. So this would now become, let me move this down a little bit. I think we need about that much more room. So now we can rewrite this, and this is going to become M over P minus 1 equals E to the negative KT minus C. Okay, but remember, we're going to use a similar trick. This is E to the negative KT times E to the negative C. But we know that this is actually just some new constant. Let's call that constant A. That's our new constant A. So now we end up with M over P equals E to the negative KT times A, right? Plus 1, right? Because I added the 1 over to the other side. Okay. So now the dilemma becomes we're solving for P. So we're going to use the reciprocal of both sides. So this now becomes P. Well, you know what? Yeah, let's do that. P over M is equal to 1 over A e to the negative KT plus 1. But I want to solve for P. So P equals M over 1 plus A e to the negative KT. And that is our logistic equation. Okay, so I guess let me move this again. So we now have that. And officially, you know what, let me make some more room. Oops, I think I lost something. Let's move this guy. So we'll get to those in a second. Okay, so that is it, is how the logistic equation came to be. So now let's just write it out officially. Formally, the logistic equation P of T equals M over 1 plus A e to the negative KT, where A equals M minus P naught divided by M minus P naught divided by P naught, and oops, and M is the carrying capacity. In general, you'll have to find, with this, you'll normally have to find K from the problem that you're given. Okay, so that is the logistic model. You know, I don't like how that looks. Let's try that. So that is the logistic. Okay, so now we're going to try it with this first problem. So we have this one, and then this one I'll move down a little bit. So this first problem says, we're not going to do a whole bunch of these, by the way, guys. I just want to do a couple. Again, this is normally a little bit easier than if you're doing it online, because you have the formula right in front of you. Sometimes you have to memorize this formula, and it makes it a little bit more difficult. So suppose the number of people in a community who are exposed to an advertisement is governed by the logistic equation. Initially, 500 people have seen the advertisement. After 1 week, 1,000 people have seen the advertisement. The total population in the community is 5,000. When has half of the population seen the advertisement? So what I'm going to do is we need to first discover or figure out a few things. We know P naught is equal to 500 because it says that initially 500 people, so they literally tell us that. We know that our carrying capacity is 5,000 because there is 5,000 people in the community, okay? The other thing we need to find is we need to find A, but it says A can be found, A can be found by using M, the carrying capacity, minus P naught, which is the initial value or the initial condition, or the initial population, I should say. So we're going to do 5,000 minus 500 divided by 500. So we should get 9. Okay, so that's our A. So what we're going to now do is we're going to substitute in what we have. They want to know when has half the population seen the advertisement. So we would like to jump straight into it. So we're going to do P of T is equal to 5,000 over 1 plus 9 e to the negative kt. But here's the problem. We don't know k and we don't know t, okay? So we technically should not be able to solve this problem unless they gave us some initial values, which they did. So they told us that initially P of 0 was 500. So we could do 500 is equal to 5,000 divided by 1 plus 9 e to the negative k times 0, right? Because this, if this is the initial population, times 0. So we have 500 is equal. Well, you know what? I'm going to divide both sides by 5,000 right now, or multiply by 1 over 5,000. So I can cancel that, divide this by 5,000. So I can get a little bit cleaner number. So now let's come over here. We're right here now, and we have, what is that? 1 over 10. Let's see here. Or I'm sorry. That's what. I think I did this incorrectly. Let's kind of go back here. I think I got a little ahead of myself. So let me see here. We have P of 0. Oh no, I see what we need to do. I forgot. I'm sorry, you guys. So we know that we know that 5,000 is equal to 1 plus 9 e to the negative kt, okay? But we know that after 1 week, so after 1 week, we already used P naught. We already used P naught up here. Sorry about that. I got a little carried away. So after 1 week, we know that 1,000 people have seen the advertisement. So we're going to do 1,000 equal to 5,000 over 1 plus 9 e to the negative k times 1 because of 1 week. So we're going to do this problem with t being in terms of weeks. So then we're going to come over here, and we now have, let me see, we could multiply both sides of this equation times 1 plus 9 e to the negative k over 1. And we could do it to this side as well. 1 plus 9 e to the negative k over 1. And then we're going to divide by 1,000 over here. Divide by 1,000 over here. You know what? I don't like putting it there. I'll write 1 over 1,000 over here. So that means that this will cancel this. That's 1. And that means this will cancel this, and that's 1. So let's do a rewrite now. And we'll have 1 plus 9 e to the negative k is equal to 5,000 over 1,000. We get 5. Okay. Let's do a little bit of quick math cleanup. So we have 9 e to the negative k 4. So then we're going to divide this by 9. So We now know that e to the negative k is equal to 4 over 9. So you could clean this up even more and take the natural log of both sides and get some decimal for negative k. But what I'd like to do is just leave it as e to the negative k and plug in 4/9 everywhere I see an e to the negative k. So now I can go back to my half-life. They want to know, so now we know what e to the negative k is worth. They want to know when has half of the population seen the advertisement. So this is very similar to half-life problems you've done before. We're going to now say that 2,500 would be half of the population. That's equal to 5,000 over 1 plus 9. Now, here's the little trick. E to the negative kt is the same as e to the negative k to the t, right? So then that means that's 5,000 over 1 plus 9, but e to the negative k, we said, was 4/9. So I'm going to put a little 4/9 right there to the t. Okay. Now you can't cancel that 4/9 and that 9 because there's an exponent of t, so you can't do that, so don't do that. But we can divide both sides or multiply by 1 over 5,000. So now we're left with 1/2, which you always will be left with when they have 1/2 of the population. 1 over 1 plus 9, 4/9 the t. Okay, so now let's flip both sides of this proportion. So 2 is equal to 1 plus 9, 4/9 to the t. Let's keep going. Subtract 1. This will be 1 over 9 is equal to 4/9. To the t. So, last step, we're almost there. We can take the natural log of both sides. This is a property of logarithms. Let's just do this. If the natural log of m is equal to the natural log of n, then m has to equal n. Well, you can also go backwards and say, well, if m equals n, then the natural log of m has to equal the natural log of m. So this now becomes natural log of 1 over 9 equals t natural log of 4 over 9, right? Because we want to get the t by itself. Now we have to divide both sides by the natural log of 4 over 9, natural log of 4 over 9. Definitely a long problem. So t equals the natural log of 1 over 9 divided by the natural log of 4 over 9. So let's see what that is in terms of weeks. Let's see here, the natural log of 1 divided by 9 divided by the natural log of 4 divided by 9. And I get 2.7, let's say 71 weeks. So in 2.71 weeks, almost 3 weeks, half of the population will have seen the advertisement. Okay, so normally these logistic model problems come in two like this. Part one is where you have to solve for k or somehow e to the negative k, and then you use information to go back and fix it. Okay, so now let's look at this next. So this next example talks about, suppose a student carrying the flu virus is on an isolated college campus of 1,000 people. So right there, we already know this is our M, right? That's our carrying capacity. Okay, we already know that. Okay, so if it is assumed that the rate at which the virus spreads is proportional to the product of the fraction of people infected and the fraction of students not infected, determine the number of students infected after 6 days. So this is what they want to know. If 50 students are infected after 3 days. So we know this is what they're looking for. And we know somehow this information is going to be used as P of 3 is equal to 50, right? So we have to figure out how to use it. Let me close it. Sorry about that, you guys. So we're going to let X be the number of students infected with the flu virus. So this is a little bit different one. We got to kind of set this up. Let's see here. The fraction of those infected. So X represents the number of students infected. Do we know how many are infected? No. So we're going to say X over 1,000. That is the fraction of people infected. Well, if this is, I guess you could say fraction of infected. Okay, so that's kind of a weird way to say it, but technically that's true. Okay, and then we could write another fraction of the students not infected, right? So I'm looking here right now, fraction of students not infected, and I'm looking at fractions of people infected. So students not infected, well, wouldn't that be 1 minus however many were in the first one, right? So that would be that situation. This is fraction of not infected, 1 minus whatever X over 1,000 was. And they want us to do a product now, right? So this is the product. The virus spreads is proportional to the product of the fraction of people infected and the fraction of students not infected. Okay, so let's see. We're going to try to do dx dt, right? Because X stands for the number of people infected. And this is going to equal to K. Now we're going to do our product. Now our product says X over 1,000 times 1 minus X over 1,000. Okay, so we're using the idea of proportional. If it has a proportional relationship versus an inverse relationship. So we have this, okay. Now, oh boy. Well, technically I could rewrite this if I wanted. This is dx dt is equal to K over 1,000. This would be another way to write it, right? Times X times 1 minus X over 1,000. Now the reason I did that is because I want to get this to be some new constant. I don't know what K is, and when you divide it by 1,000, it's just going to be some new K. So let's just call it K hat. So let's call this K hat. So let's rewrite this as K hat times X, 1 minus X over 1,000. You know what? I'll write it in green so that you notice that it's a little bit, we fixed it. It's actually, it came from this. Okay, so now we have our new equation, dx dt equals K hat X 1 minus X over 1,000. Okay, now technically, we now know that the carrying capacity is 1,000. Oh, so what is this right here, by the way? What is this formula right here? Well, let's look back. This is a constant times X times 1 minus X over 1,000. So if we come over here, we just look back. Oops. Where did I find it? That is right here. This is the logistic equation, okay? P divided by some carrying capacity, M, some constant times P, right? So this is the same as this. So this is just the logistic model. So we were doing this to see or to make sure that it was governed by the logistic model. So that means that we now can solve this in a faster way. We have X equals the number of infected, 1,000, the carrying capacity, divided by 1 plus, oops, I got to find a few things first. So before we jump into this, let me find a few things. We know M is worth 1,000 because it's the carrying capacity. We know A is worth M minus P naught over P naught. But they kind of snuck it past us. They said the carrying capacity is 1,000, we know that. But they said 1 student, so the initial value was 1, right? So we ended up getting 999, okay? So now we can use our logistic equation. Let's go back up here. The logistic equation says A equals, or the number, I'm sorry, P of T is equal to M over 1 plus A e to the negative KT. So all I'm doing is I'm looking at the logistic equation right here. Okay. And we're just going to write carrying capacity. X equals carrying capacity of 1,000 divided by A, but in this case, A was 1 plus 999, that's our A, right? E to the negative K times T. So that's our formula. That's the formula that we have. Now we can use this initial condition that they talked about right here of 50 students are infected after 3 days. That's are not an initial condition, but not the first P naught, but it is a condition that was given to us to help us with the problem. So we can now say that 50 will be infected after 3 days. -3K, right? So let's clean this up a little. Let's see here. We could flip both sides. So this would be 1 plus 999 e to the negative 3K equals, and then we would have 1,000 divided by 50, I believe. And that should be 20. So we'll get 1 plus 999 e to the negative 3K is equal to 20. Okay. So then let's clean this up even more. We have 999 e to the negative 3K equals 19. Okay. Divide both sides by 999, so we have e to the negative 3K is equal to 19 over 999. Okay, so hopefully you guys, I didn't lose you here. This is kind of a long-winded process. You know, maybe I should have isolated it as e to the negative K to the 3. This I think would be better. And this is 19 over 999. Then I can take everything to the 1/3 power. So that'll just give me e to the negative K is equal to 19 over 999 to the 1/3 power. So we now have our e to the negative K. So now what we need to do, this is a little bit, it's going to be quite ugly, is we are now going to go back to x equals 1,000. The number of people infected will be x, right? So I'm going way back up here, and it says let x be the number of students infected with the flu virus. So how many people are going to be infected with the flu virus? Let's see here. It says determine the number of students infected after 6 days. Okay, so we're going to do 1,000. 1 plus 999, 19 over 999, and this will be, remember, t over 3, right? Because we know that e to the negative k is, let me plug this in a little bit. Steps here. Okay, so this, I think I skipped a step. I don't want to lose you guys on this one. So this is 1,000 over 1 plus 999, 19 over 999 to the 1/3, to the t. So we could clean this up a little bit better. And that's where I got the t over 3 from, okay? However, do we know what t is? Well, they said 6 days. So we're going to do x equals 1,000. So after 6 days, x equals 1,000 over 1 plus 999, 19 over 999, 6 over 3 for our power. So basically squared. And you guys take a minute, plug that in your calculator, but you should get 735.3 people. So that's, again, I hope you guys can see that the logistic equation can get a little out of hand because you have to basically do two problems. You have to first solve for e to the negative k, and then you have to solve for whatever the request is for the problem, or not solve for, but find the value of the population. How many people infected, how many people have heard the rumor, how many people have seen the advertisement, whatever the case may be. But hopefully this gives you guys a little bit of insight on how to do some of the logistic problems that you might see in your homework, or if you go on further into other differential equations. Okay, so I think that's going to be it for this video. I'm going to try to make another video for 10.1 and 10.2, and I'll be sending that out to you in a little bit. Maybe not today, maybe tomorrow morning, but okay, you guys, that'll be it for this video.